In the previous video, we have defined lifting and find some examples of lifting. And we have also proved that whenever we have proved by examples that whenever P is a covering map, then the paths can be lifted to paths. We have defined 3 different paths and proved that their liftings are also path. So now we prove this result in general. So we prove this lemma. So let us take P to be a covering map from E to B. Then now here we will prove that any path F from the interval 0, 1 to B means any path in the space B which is beginning at point B0, let us say, then this path has a unique lifting to a path F curl in space E, and this path will begin at point E0, where this E0 is the point whose image under the mapping P is the given point B0. So let us prove this. Now because this mapping P is a covering map, so we can cover the space B by open sets U, each of which is evenly covered by P. So cover the space B by open sets U, each of which is evenly covered. Now this thing is possible because for a covering map, every point of B has a neighborhood which is evenly covered by P. So if every point has a neighborhood which is evenly covered by P, so we can find out an open covering of the space B by the open sets U, and each of these sets U is evenly covered by the mapping P. So we can find now a partition of the interval 0, 1. Let us say this is the partition S0, S1 up to Sn, such that for each I, image of the set, image of the closed interval Si to Si plus 1 that lies in some open set U. Out of this open covering. Now this thing is basically possible by Lebesgue number lemma. So Lebesgue number lemma says whenever we have a mapping P from E to E which is continuous map, continuous onto map, and we have open cover of the space B by open sets, then we can find a partition of interval 0, 1 such that f of Si to Si plus 1 is contained in some open set of this covering, open covering. Now F is a path in the space B which is beginning at point B0. So here we have to define a lifting. We have to prove that there exists a unique lifting map F curl. So we will define here this lifting step by step. Firstly, we define the lifting at point 0, because we know that whenever we have mapping P, let us say this is the mapping P from E to B, and we have mapping F from closed interval 0, 1 to B. This is our given path. Now we need this path F curl from 0, 1 to E. So we have to define F curl on interval 0, 1, which goes to space E. And this should be a path which is unique lifting of F. So firstly we define at point 0 by E naught. Then we suppose that F curl S is defined. F curl is defined for all points S lying between 0 to Si. Actually, we have partitioned our interval 0 to 1 into the points S0, S1, Sn. Let us say this is the partition of interval 0, 1. So this point is S0, S1, S2, Sn. So we have defined F curl at this point 0, and we have assumed that F curl is defined for all S lying in 0 to Si. So let us say F curl is defined on this interval 0 to S2. And now we will define F curl from S2 to S3. So we know that F of Si to Si plus 1, because of Lebesgue number lemma, this is contained in some open set U. And this U is evenly covered by P. So let us take V alpha to be partition of P inverse U into slices. Let this be partition of P inverse U into slices, which means P inverse U is equal to union of V alpha. V alphas are all disjoint open sets, and V alpha is homeomorphic to U for each alpha. Now since we know F curl of Si to Si plus 1 contained in U, so F curl of Si that lies in one of these sets V alphas, because we have defined lifting F curl of F on the interval 0 to Si, and on the interval 0 to Si F curl is lifting. It means on the interval 0 to I we have this P circle F curl, that is F on 0 to Si, and we are saying that F of Si to Si plus 1 is contained in U, which means P circle F curl of Si to Si plus 1, that is contained in U. So it means F curl of Si that lies in P inverse U. So this lies in one of the sets V alphas. Let us say that set is V naught. Say this is contained in V naught, because we know this F curl Si, this is contained in union of V alphas. So now we define F curl S on the interval Si to Si plus 1 by this equation. This is P restricted to V naught, and then we take its inverse at point Fs. So here the basic idea is that this point Fs, whenever S is lying in the interval Si to Si plus 1, this is contained in U, and we know V naught is homeomorphic to U, and P, which is restriction mapping to the space V naught, this is basically the homeomorphism from V naught to U. So for this point Fs, there is a unique point in the inverse image, means there is a unique point in the space V naught, and that point we will denote by F curl at S. So for each point Fs, let us see in this diagram, we take a point S here in the interval Si to Si plus 1. Then we know f of s belongs to U in this space V. Then this U is homeomorphic to V naught here, and the homeomorphism is the mapping P restricted to the space V naught. So that point has exactly one point in the space V naught, which is inverse image of this point here. So we define F curl at this point S to be that point in the space V naught. Now this F curl, this will be continuous, because this P restricted to V naught, this is a homeomorphism. So its inverse map, that is also a homeomorphism. So this is continuous on the interval Si to Si plus 1. So now we have defined F curl on the interval Si to Si plus 1. So continuing this process, we can define this F curl on the next interval and so on. So continuing in this way, we can define F curl on whole of the interval 0, 1. Now on each of the subinterval F curl is continuous, and by pasting lemma we can show that F curl is continuous on whole of the interval 0, 1. Now because we have defined F curl to be P restricted to V naught inverse at Fs, so by this definition we can see that P circle F curl is F, which proves F curl to be the lifting of F. So now this proves the existence of lifting. So now we prove the uniqueness part. Now as we have proved the existence step by step, we will prove the uniqueness also by step. Now suppose F curl, double curl, this is another lifting. Suppose this is another lifting which begins at E naught. Now since F curl is the lifting which begins at E naught, because we have already defined F curl at 0 is equal to E naught, so that is the lifting which begins at point E naught. So we know this thing, F double curl at 0, this is E naught, and F curl at 0, that is also E naught, that we have defined. So it means at 0 the both mappings are same. Now we suppose that F curl is equal to F double curl, on the interval 0 to Si. So we will prove these two are equal on the interval Si to Si plus 1. So let us suppose V naught be the same set as in the existence part. Then for any S in the interval Si to Si plus 1, we have defined F curl at S to be P restricted to V naught inverse image at off point Fs. Now what is the value of F double curl S? What should be the value of F double curl S for this S? Now what should be the value of F double curl S? Now since F double curl, that is also a lifting of F, so it must carry the interval Si to Si plus 1 into the set P inverse U, which is union of V alpha. So F double curl carries this interval into the set P inverse U, because this is a lifting, which means P circle F double curl, this is F. So F double curl, if F double curl carries this interval Si to Si plus 1 into the set P inverse U, then only P circle F double curl will be F. But we know the slices V alphas, they are open and disjoint, and the set Si to Si plus 1, this is connected set. If this is connected, then its image under F double curl, that is also connected, because F double curl is a path, so that is a continuous mapping. The continuous image of connected set is connected, so this is a connected set. And we are saying that F double curl of Si to Si plus 1 is contained in the set union of V alpha, and V alphas are all disjoint and open. So it means F double curl of Si to Si plus 1, this is contained in some set V alpha entirely. This whole set entirely contained in one of the sets V alpha. So let us say that is V alpha. But also we know that F double curl Si and F curl Si, they are equal, because we have assumed that they both of them are equal on the interval 0 to Si. But this point F curl at Si, this belongs to V naught. So the point F double curl Si belongs to V naught. And we are saying the whole of the set F double curl from Si to Si plus 1 is contained in only one of the V alphas. So it means whole of the set F double curl from Si to Si plus 1, that is contained only in V naught. So it means for each S in Si to Si plus 1, F double curl at S must equal some point Y of V naught. So this is equal to some point Y of the set V naught. And this V naught lies in, so this Y, some point Y of V naught, which lies in P inverse of Fs. Because F double curl is a lifting, so P circle F double curl should be equal to F. So if Y is F double curl at S, That means y belongs to P inverse of Fs. But we know V naught is homeomorphic to U. So for each point Fs in U, there is only one such point Y in the space V naught. And that point is, but there is only one such point Y. And that point Y is basically P restricted to V naught inverse at F of S as the definition of F curl. And we are saying that F double curl should be equal to only this point Y. So it means F double curl at S, this is equal to F curl at S for all S in Si to Si plus 1. So assuming both of F curl and F double curl equal on 0 to Si, we have proved that they are equal on the interval Si to Si plus 1. Continuing this process, we can prove that these two are equal on whole of the interval 0, 1. So this completes the proof of the lemma. So this lemma proves that whenever we have a covering map from E to B, then any path in space B starting at point B naught has a unique lifting in space E starting at point E naught, where this E naught is inverse image of the point V naught. Or we can say E naught is the point whose image is V naught.